This video is going to give you a brief introduction to mathematical polynomials. Polynomials are a family of functions that we use in a wide variety of contexts in mathematics because they're well behaved and we're able to build up some pretty complicated behaviors by using these pretty simple building blocks. What I've got written on the board right now is an example of the form of a polynomial. A polynomial is built up of many different terms. It could be just one or it could be a whole bunch. And those terms all have a similar structure. A single term in a polynomial, right now we're writing a polynomial in one variable. So a single term in a polynomial consists of the variable, which in this case I've used x as the variable, a coefficient, and a power. Okay, so polynomials consist of distinct pieces. Each piece is different. This is a single piece is called a monomial, which is the variable that we're concerned with, and it's raised to a power. And that power is an integer when we're dealing with polynomials. Okay, so each term in the polynomial consists of a monomial, x to the n in this case, x to the n minus 1 here, and then a coefficient, which is a real number. Okay, so when I look at this polynomial, I've got a lot of different spaces, a lot of different kinds of monomials that I could build a polynomial from one. Each one of these different terms has a different degree, a different size power. The smallest or simplest thing that would appear in a polynomial function would be a constant term. And then as we increase the power that we have in the exponent here, we get more and more complicated monomial terms. So this is the kind of shape of a polynomial. What I'd like to do is just show you some simple examples for these, and then we'll look at the ways that these polynomials can be manipulated. Okay? So remember, we've got monomials, and those monomials have coefficients. A polynomial is built by just adding a bunch of these things together. So some examples of polynomials. You could just have a constant function, p of x just being 1. That's an example of a polynomial function. It's not a very interesting one, but it does qualify as a polynomial. Another example might be 3x squared minus x plus 6. That's an example of a polynomial function. In this case, it has 3 terms. It has the constant term 6, the term negative x, and the term 3x squared. Notice that when I write down the polynomial, I'm writing these terms in a specific order. This is called the standard form or the canonical form for a polynomial. And what we usually do is we draw or write the highest degree terms first and write all of the other terms in descending order and end with the constant term. By using this type of ordering for our polynomial, we can keep track of the highest and lowest degree terms. The degree is the value, the size of the exponent that we see in a certain term. We can keep track of the degrees, and it helps to organize the polynomial. It makes it easier to manipulate them or add them together. So this is an example of a second degree polynomial. It has a x squared term, an x term, and a constant term. We could also have x squared minus 1. This is another example of a polynomial. Here, there's no x term that appears, but this is still a second degree polynomial. Okay? Having a coefficient of 0 is perfectly reasonable, and it's something that we actually need to worry about in situations where we say need to divide polynomials. Okay? All right, so we have the polynomials, we have the terms of the polynomial, we have the coefficients of the polynomial, and we have this word called the degree of the polynomial, and the degree refers to the highest order term that appears. Okay, so the highest exponent that we see on the variable x, that's called the degree of the polynomial. If we want to deal with polynomials, we might want to put them together to combine them in different ways. So we might try to add polynomials. And for adding polynomials, it's very helpful to use standard form. And all we need to remember to do is to combine like powers. Or combine like terms. Okay, so if I was going to add two polynomials together, if I wrote them down in standard form, that would help me to organize the computation. And then all I would do would be to combine like powers or combine like terms in the two polynomials, and that would be how I would add them together. So let me give you an explicit example of that. I'll write down two polynomials. I'll write down x cubed minus 3x squared plus 6. This will be the first polynomial that I'm going to write down. And then I want to add that to another polynomial, which I'll write as x to the fourth minus 6x cubed plus x squared minus 2x minus 6. Okay, so I'm thinking about adding this third degree polynomial and this fourth degree polynomial. So I've written them both in standard form. I've put the highest degree terms first and the lowest degree terms last. So adding them together simply consists of finding the like terms and combining their coefficients using regular arithmetic. All right? So if I look at these two polynomials, I see that I only have a single x to the fourth term. So there's nothing to add that to in the first polynomial. So that will just remain in the sum of these two polynomials. So I expect my answer to have just one x to the fourth. Okay? Next, I go to the next lowest degree. So I look at the x cubed terms, or the x to the third power terms, and then I want to combine those using regular arithmetic. I have 1x cubed in the first polynomial, and I have minus 6x cubed in the second polynomial. If I combine those together, I have positive 1 minus 6. I should expect to see negative 5x cubed in the x cubed term. If we look at the x squared terms, x to the second power, that's our next term that we want to combine. We have negative 3x squared in the first polynomial, and we have positive 1x squared in the second polynomial. So negative 3 plus 1 leaves us with negative 2x squared. And then we want to combine the x terms. I see no x terms in the first polynomial, but I see negative 2x terms in the second polynomial. So we'll have negative 2x in our sum. If we look at our constant terms, we have a positive 6 and a negative 6, and those are going to cancel perfectly, leaving us with 0 as our constant term, which we can either write down explicitly or we can leave off. Okay? If you have a coefficient of 0, you can leave that out of the solution. You don't need to write it down. Okay, so the sum of these two polynomials would be this polynomial right here. If I wanted to subtract polynomials, I can just distribute a negative sign and then add the polynomials together. So let's do a simple example of that. X squared minus 2x plus 3. And say I want to subtract from that the polynomial, let's do minus 2x squared plus 4x minus 1. Okay? So I have a second degree polynomial here, and I'm subtracting another second degree polynomial here. We can distribute the negative sign throughout each term of the second polynomial and then add them just like we did in the previous example. So just by combining like terms and adding or subtracting their coefficients. All right, so let's distribute this negative sign. We get x squared minus 2x plus 3. That hasn't changed at all. And we're going to subtract from that 2x squared minus 4x. And finally, distributing that negative sign all the way across, we get plus 1. Once we've distributed the negative sign, we simply add all these terms together by combining like terms. We have 1x squared here and negative 2x squared here. Combining those will give us negative 1 times x squared, which I just write as negative x squared. Combining the x terms, we have a negative 2x and a negative 4x. Putting those together gives us negative 6x. And the constant terms, we have a positive 3 and a positive 1. Combining those will give us positive 4. So that's the basic idea when it comes to adding or subtracting polynomials. We simply organize them in standard form. That keeps everything arranged so that it's easy to figure out which parts go with which. And then we combine like terms. In addition to standard form, we also have something called factored form, which works for some polynomials and helps us to solve polynomial equations. Before we start talking about factor form, though, let's look at what happens if we wanted to multiply polynomials. Right? And here we're going to start with some easier, very, very simple examples and build up from those. The basic procedure when multiplying polynomials is to use the distributive property. I'll say until everything is mixed. Okay, so to give you an example of this, what I'd like to start with is I'd like to start with two very, very simple polynomials. Maybe polynomials with just first degree terms, so constant terms and maybe x terms. So let's say that we have x, just an x by itself, and we want to multiply that by 3x plus 2. Okay? When we're going to multiply polynomials, it's important that we use the distributive property to help unravel all the different options, all the different possibilities we have when multiplying things around. Here, in this simple situation, we have an x, but nothing else. So this is a single x multiplied by a polynomial with two terms. A constant term with the 2, and an x to the first power term with this 3x. What I want to do to complete this multiplication is to distribute the x across these two terms. So the distributive property allows us to split this up and to remove the set of parentheses that we see. When we multiply two x terms together, we have to use properties of exponents to track what happens to the terms themselves, and then we use arithmetic to deal with whatever numbers appear in the coefficients. So I have x multiplying this first term. The x and the x, when I multiply those together, I use the properties of exponents to figure out what type of term results. So if I just see an x, I want to think about that as an x to the first power, just one copy of x. When I multiply these together, the exponents that appear add together. So x times x gives me x squared, and the coefficient is left alone. So I get 3 times x squared. And then using the distributive property, we need to take this x and also multiply by the 2 term. Since the 2 doesn't have any x attached to it, multiplying by x is just going to give us one copy of x. So we get 2x. And that's basically it. The complexity arises if we have bigger polynomials or more terms in our polynomials to complicate all the different options that might appear with the multiplication. Okay? So let's do a slightly more complicated example, and then we'll start to build off of that. Here we're going to have two polynomials, and each of them is going to have two terms. Let's try maybe an x plus 1 and then an x plus 2. So our first polynomial is x plus 1, and our second polynomial is x plus 2. Here I'm going to use the distributive property, but I'm going to need to use it more than once to kind of take care of everything that appears. I'm going to show you some intermediate steps as I go, but as you develop more competence, more comfort with this process, you can often do this without including too many intermediate steps. So I'm going to set myself up with an equal sign where I'm going to put the final answer, and then below I'm going to show you some intermediate steps where I'm building up all the different pieces of the computation. So the first thing I'm going to do is I'm going to use the distributive property to split the multiplication of the first polynomial and the second polynomial. So I'm going to take the whole first polynomial, and I'm going to use the distributive property to multiply it by each of the terms in the second polynomial. So I'm splitting up this big multiplication operation into multiplication of a polynomial times a single thing, which is kind of like our first example. Right? So this first step, I take this x plus 1 and I multiply it across to each term in the second polynomial. So we have x plus 1 is going to multiply the first x that we see here, plus x plus 1 is going to multiply the 2 that we see here. Okay? So we've used the distributive property to kind of split that into two pieces. Then we're going to use the distributive property again, and we're going to split each of the terms that we've broken off so that it multiplies each of the terms into the first polynomial. Okay? So this first term, when I use the distributive property on it, I get x times x, which gives me an x squared. When I see multiple x's appearing, I'm going to just add their exponents together. And then I get an x plus 1. So I get x squared plus x. Okay. And in the second term, I'm going to use the distributive property here to multiply the 2 times each of the terms in the first polynomial. So I'm going to get a 2x, and then 2 times 1, I'm also going to get a 2. So you see that when we use the distributive property, we kind of unravel it until all of the terms appear on the same level, till we've dealt with every set of parentheses that we have. Right? Once we've done that, then we can combine like terms. I see a single x squared, an x, a 2x, and a 2. Of those 4 pieces, 2 of them are the same kind of term. 2 of them have the same power of x appearing. So I'm going to add those together and combine their coefficients. And then the other terms, each one only appears once, so I'll add that in as a different kind of term in the polynomial that results. Okay? So that's kind of a simple example of how you would multiply polynomials together. I'm going to do the same thing, but I'm going to build up yet a more complicated example. So we'll deal with higher degree polynomials, and we'll put in some more complicated signs as well. And before I write down this example, I'm going to kind of give you a more concrete direction for what we're doing. We're making sure that we use the distributive property until everything is mixed. What we need is every term in the first polynomial must multiply every term in the second polynomial. Okay, so that's what's required when we do this multiplication of polynomials. All the things in the first polynomial have to multiply all the things in the second polynomial. Once we've combined all these things together, then we simplify by combining like terms. Okay, so we're going to multiply everything by everything else, everything in the first polynomial by everything in the second polynomial. Then we'll simplify by combining like terms. Okay, so for our third example, let's do maybe a quadratic polynomial and multiply that by a first degree polynomial. So one of our polynomials will have 3 terms and the other polynomial will only have 2 terms. And we'll see what happens with that. So let's make, how about 3x squared minus x plus 1. And as our second polynomial, maybe we'll do x minus 2. Okay. So, just like before, I want to use the distributive property to help split these things up into their various pieces. And then I'm going to combine all the results and see what happens. So we need to multiply every term in the first polynomial by every term in the second polynomial. So a way to keep track of that would be to use the distributive property to split the multiplication of the first polynomial into each of the 2 terms in the second polynomial. So what we need is to take the first polynomial, 3x squared minus x plus 1, and we're going to multiply that by x, and then we're going to multiply it by negative 2. So I'm thinking about negative 2 times that whole first polynomial. 3x squared minus x plus 1. Note that I changed the order here. I moved that polynomial to the second term, and that's legitimate. That's okay because multiplication is commutative. You can change the order of the things that are being multiplied together, and that won't change their value. The reason I did that is that I have this minus 2 here, and it's a little bit less awkward to multiply negative 2 by everything than to put the negative 2 afterwards, because then I might get confused with whether I'm dealing with multiplication or subtraction. So that's just to help me organize things. Okay, so we've used the distributive property once to multiply everything in the first polynomial by each of the things in the second polynomial. And next we're going to use the distributive property again to figure out all the different pieces that we're going to end up with. So we need to distribute the x across each term in this quadratic, in the second degree polynomial. So we have x times 3x squared. The x's there are going to combine, and we're going to get 3x cubed. We had x squared here, and another power of x here. We add the exponents to give us an x cubed term. Multiplying the x times this negative x gives us negative x squared. Okay? And then finally, we get x times 1, so we get plus x. Next, we're going to multiply this negative 2. We're going to distribute that across everything in this set of polynomials, or this polynomial right here. And there we're just dealing with the coefficients, so let's multiply those across and see what happens. So we get negative 2 times 3, and that's an x squared term, so we end up with negative 6 x squared. Negative 2 times negative x gives us positive 2, and that's an x term. And then negative 2 times 1 gives us negative 2. Okay. So we've kind of distributed, and these are all the terms that are in the product of those 2 polynomials. Next, what I'd like to do is just combine everything into standard form. And once it's in standard form, we'll have one of the simplest representations of this polynomial, one of the simplest ways to write it down. So the highest degree term here is an x cubed term, so we'll write that first. We have 3 x cubed. It looks like we have 2 different x squared terms, so we're going to combine those like terms. We have negative 1x squared in this grouping, and then negative 6x squared in this grouping. So we have negative 1 and negative 6 gives us negative 7x squared. And then for x terms, we have a positive 1x and a positive 2x. Those combine to give us 3x. And then we have a single constant term right here, which is a negative 2. So we'll put that on the end. That gives us the product of these polynomials. Okay, so that gives you kind of a basic idea of how you add, subtract, and multiply polynomials. In the videos that follow, we're going to explore some more complicated ideas that involve polynomials. One of the big features that we're going to look at is a process called factoring. Now, factoring starts from a polynomial in say, standard form like this, and it breaks it down into smaller pieces. Okay, so we'll look at a few different situations where we can do that. Okay, so that completes this video, which gives you a basic overview of the rough algebraic manipulations of polynomials, how you would add them, subtract them, and how you would multiply them together. As long as you keep your work organized, this isn't too hard. It just takes a lot of practice to make sure that you're using the distributive property correctly so that you get all of the pieces that you need. It's easy to miss something when you're multiplying things up. Okay, so that completes this video.